Hey guys, welcome back. So today we're working on the storm responder generator. This machine I recently made a video on. It had engine issues, but at this point the engine runs well and the generator makes power. So this is pretty much ready to go. That said, there is a problem, and not specifically with this machine, rather every machine ever made that uses this style of generator. It is a very robust generator. The stator and rotor almost never fail, and the THD is actually fairly low. But the weak point is the bridge rectifier in the voltage regulator. This part commonly blows out and usually not a big deal. You just buy a new one, install it, and the generator will make power again. The problem is this part has recently been discontinued. It is no longer available, and I've been receiving a lot of emails from people asking where they can buy that part, and the answer is you can't. So if we don't come up with an alternative to the OEM part, I would say tens of thousands, if not hundreds of thousands of this model will eventually stop making power and end up in the trash. So the goal today is to find an alternative to the OEM part. So let me get you set up a little bit better and get going on this. All right, so first things first, I do want to get this started with the OEM regulator installed. Now, this is not an automatic voltage regulator in this machine. It's just a voltage regulator. So that means the voltage is going to be high under no load, around 130 volts, and under full load, it's going to drop by about 20 volts. Now, this, although it is repaired, I actually haven't done the load test on it. And if I remember right, the engine speed is a little slow. So I'm going to get it started as is. Likely I'll bump that speed up a bit, and we'll double check the no load voltage. And assuming everything's good, we'll get the machine shut down. We'll turn it around, get the end cover off, and pull out the OEM part and see what we can come up with. All right, so let's get this started real quick. I just want to get a baseline with the OEM part as far as the voltage goes. So the fuel's connected, choke's on, ignition's on. The light's plugged in and turned on as well. So we've got our baseline, the engine. It is a little fast. Ideally, it would be closer to 61.5 hertz, but that is not the focus of today. What we wanted to know is the voltage, and it's at 133 volts with the OEM part, which is high, but normal on this type of machine without an automatic voltage regulator. So let's get this spun around, get the OEM part out, and try some alternatives. And there is the voltage regulator in question. So, the machine we're working on today is a storm responder, but this generator and bridge rectifier brush combo, it's found on a lot of different machines, including Troy-Bilt, Craftsman, Briggs Elite, and I'm sure a bunch of other brands. So whatever we figure out today, the same can be applied to those as well. All right, so we've got the OEM part out, and obviously it's in good condition, at least it works. But when looking it over, I can see that the brush here on the left, for whatever reason, it is worn slightly more than the brush on the right. So that actually brings up a good point. You know, we can build or buy a bridge rectifier, but the brushes, you know, that is part of the discontinued parts. So if the brushes fail, either due to wear or in the case of this set of brushes, user error, where you actually break the brushes off, you know, what are you supposed to do? So the answer, I think, is this set of brushes right here. This is actually from a Generac XL or EXL series generator. And those machines were actually made at a time where Briggs owned Generac. And even though this does not have a bridge rectifier built onto it, the form factor of the brushes, it is identical to the original part. So we can actually bolt these on to the storm responder and theoretically feed power to the rotor. Now, the only problem is that this set of wires right here, this is the DPE winding. This is the power source that feeds the rotor, and this is AC. It has to be rectified to DC before it goes to the brushes, and that is the purpose of this board right here. We have 4 diodes. This is a full bridge rectifier, and that will feed DC to the rotor. So what I'm thinking is that we should use the Generac XL series brushes along with a standard bridge rectifier. This one came from Amazon. It cost $1. So yeah, I'm not holding my breath on this one. There weren't a lot of details as far as what diodes are in here, but there are 4 diodes. The only stats listed were 1,000 volt rating at 50 amps. And from looking up this particular diode right here on the OEM part, this is rated at 1,000 volts also, but only at 30 amps. So theoretically, this is more capable, but it's still an unknown. You know, we have no way of proving that. And of course, with diodes, there's a lot of other characteristics besides those two. So will these perform as the OEM part? I'm not sure. And even if they do, you know, how long will they last? Because this bridge rectifier has one extra part. This is a metal oxide varistor, and it's on the DC output side of things. Now, normally, this does nothing. But if there is a surge, then this actually clamps down between the positive and negative and kind of quenches that surge and protects the diodes. This does not have that. So it may not last as long as the OEM part, or potentially it'll instantly fail. But that is what we're going to find out. So I'm going to use the Generac XL brushes with the Amazon $1 rectifier. We need to make up some cables, connect everything together. Then we'll start the engine again and see what we get. So to make this work, we don't have to do a whole lot here. We already have these spade terminals right here, which is the AC output, and that gets connected to these spades right here. It doesn't matter which one goes where because it is AC, but on the DC out, it does matter. The terminal here that's rotated differently from the other 3, that is the positive. So we need to feed that to the positive side of the rotor, which is the closest one to the ball bearing. So when we get this mounted, we're probably going to mount it something like that. So the positive will go right there, negative will be in the back. And to make this all work, we do need spade terminals here on a wire connected over to the bridge rectifier. And as you can probably see, the space is pretty tight. So you do need these right-hand terminals that we have right here, these 90-degree ones. So I did find some wires from a generator that didn't make it that already have those terminals on it. You know, if you don't have such a thing, you can actually buy them on Amazon, actually a whole kit for about $27 that will allow you to crimp these on to pretty much any wire. So we do need to add some spades to the other end to connect to the DC output. And at that point, we can give this a go. So this wire, it is pretty thin gauge, but the current flow for the rotor 2 is actually pretty low. About 2 amps, actually a little bit less. So you don't need any crazy thick wire to do this. So we'll get those stripped back. And add the spade terminals. So we'll get these connected. I'm going to install it like this. So we'll use the red to indicate the positive. And the blue is the negative. And you do not need to make these excessively tight. Yeah, this is screwing into aluminum. It strips out very easily. So just snug it up. You should be good to go. So let's just double check this real quick. Make sure the brushes are making good contact to the slip rings. Now usually this rotor is about 23, 24 ohms. Through the brushes, it's going to be a little higher, but we want to see something in that ballpark. And yeah, we're at 31.8 ohms, so that is good. We'll check it for ground fault, and there is none. So this Generac set of brushes, I think it's going to work just fine on this style generator. All right, so let's get the bridge rectifier connected, starting with the DC output. So we'll connect the positive brush to the positive output. And then diagonal to that is the negative output. And then these wires get connected. Doesn't matter which terminal of the ones remaining. This is ACN. So we'll get that one plugged in there. And the other one right there. Like that. So I'm going to leave this as is. We'll get it restarted and double check the output. All right, let's try this again. We have the same light plugged in and turned on, kilowatt. The difference is we have the Generac set of brushes and the $1 Amazon bridge rectifier. So the fuel is on. Let's turn the choke on, ignition on, and let's see what we get. All right, so that worked fine. I guess the question is, without the metal oxide varistor, did we just blow out a diode, shutting it down when that field collapsed? So Let's get it restarted. Ignition's back on, choke's on. Yeah, I've got to be honest. For $1, I didn't expect a whole lot, especially when the OEM part sells for about $50 to $60 if it was available. And although, we only ran it for a short time, this has a lot of promise at a fraction of the cost. So I do want to get the correct metal oxide varistor ordered up. We'll add that to the circuit just to add that little bit of extra protection. But I'm thinking, even before I do that, I do want to take some more measurements on the power feed to the brushes. I want to see what the voltage is at, as well as the amp draw. So let's get a couple meters hooked up. We'll do another quick test and go from there. All right, so let's get this connected to the multimeters. So I'm going to remove the positive lead from the bridge rectifier. And I want to feed it through this meter right here so we can measure the amp draw. So I'm going to connect a lead to the output of the bridge rectifier. The other end will go to this red lead here on this meter. And then we'll take the other lead from the meter and we'll connect that to the brushes. So like that, that'll give us the current draw to the rotor. So that is good. Next, I do want to measure the voltage. So I'm going to connect up another lead to the positive output of that rectifier to the positive on this meter right here. Onto that lead, like that. And then we need the negative, so we'll connect this up to the negative lead on the multimeter. So like this, we can measure now the voltage and the amp draw. And I think just to complicate things a little more, let's get the oscilloscope out and just take a look at the waveform feeding that rotor. Yeah, I wouldn't say this is very safe, but looks like we should be good enough. Now, when the engine starts, it could throw one of these leads off. So if that's the case, we're going to have to shut things down and reset. But as we are connected right now, we should get a read on the output. Using the oscilloscope, we'll see what that waveform looks like going to the rotor. We'll see what the voltage is, as well as the amp draw. So let's get the engine started. All right, one last check on the wires. Looks like we're good. Nothing's going to short out. So let's get the engine started. The fuel is on. Choke is on. Ignition's on. And the table's a little bit high. That's okay. Contact. All right, so that did not go as planned. The generator did not power up. So either I connected something incorrectly, or potentially we blew out the bridge rectifier already. So let's get this disconnected, take a few quick measurements and see what happened here. All right, so we'll put this back to normal mode here. Set that to test diodes. All right, so I'm going to put the positive lead here on the output, the DC output. And then if we put this negative lead on either of the AC inputs, we should not see current or a voltage drop. And we don't. So that would suggest that these diodes are probably working. Let's try it the other way. And like this, we should see a voltage drop from either one of the AC inputs. We do. And we do. So the diodes right here seem to be fine. Let's try the negative output. Do the same test. We shouldn't see any voltage drop on the AC inputs, and we do not. And with the positive, let's try this again. Positive on the negative output, which is right here. We should get a voltage drop from both the AC inputs. And we do. So the bridge rectifier is not the problem. Likely I didn't have something wired quite right. So I'm going to get everything connected back, and we'll try this again. All right, take two. Choke on, ignition on, contact. All right, so a much better result this time now that things are connected correctly. We were generating power. And for the most part, I kind of saw what I expected, except for the current draw. I was expecting that to be less than 2 amps on most Honda clones. That's what it is. But this is not a Honda clone. It was actually pulling 5 amps through the bridge rectifier. So initially I was thinking heat dissipation on the bridge rectifier wasn't really a concern, but given the amp draw, that is maybe more of a concern than I thought it was initially. The original part had no heat sinking. It actually relies on the airflow through the rotor. There's actually a fan on the back side of the rotor that pulls cool air in through the cover, and that, I assume, was keeping this bridge rectifier cool. So mounting this component, I would say, is going to be critical, and we're going to need to do some extended testing just to see how hot this gets. There's really no great place to heat sink it given the setup that we have here. So I think we're going to have to rely on air cooling. Whether that's going to be adequate, not sure, but we're going to find out. So to get this mounted, we have a couple options here. I guess initially, I was thinking this would be a good location. This is just a through hole. It is not threaded, but we could run a bolt and a lock nut to secure this in place. And like that, we are going to get some heat sinking as well as some cooling from the airflow. Although we're not directly in the flow of air, this potentially is an option. The only issue is that these ribs turn up right here. So to use that hole, it wouldn't mount very well. So we'd actually have to drill a new one, right about there. So definitely an option. Another option would be down here where the ground wire is. This is actually a threaded hole, and I think would work pretty well. But we would need to modify things as well. We have this little locating pin right here, which is going to prevent this from mounting properly. So if we wanted to use this location, we would have to cut this off. So, both of these I would say are options, but there is a third one, which I kind of like, because some of these, not the storm responders, but some of these Briggs generators did have AVRs, And they actually mounted the AVR board right here in these slots, and the electronics kind of hung down in the air stream. So I asked my son to just print up a blank with a hole so that we could mount the bridge rectifier. And like this, we can actually mount it like that. And these are actually tapered. So if you push it in, it kind of locks in place. And once you add the end cover, that's going to ensure that this board can't slide out. So, instead of just mounting it right to the plastic, I'm actually going to use a spacer to hold it off a bit so that we get some airflow on the surface as well. So to make this work, we are going to need 90-degree connectors because it's pretty tight in here. And these connectors, although technically we could probably make them work, I think if we did 90s all around, it would make a better fit and also allow us to space it like we want. So yeah, let's get some 90-degree connectors on here. We'll give this a try, see how we make out. All right, so we'll cut those ends off and strip these wires again. Maybe. All right, so I've already got one of these connected. We'll just do the other. Okay. So that gives us what we need. These wires, they're still too long. I think in the end we'll figure out what the correct length is. But for testing, that should give us what we need. So let's get the bridge rectifier mounted to that blank with a spacer. Get everything plugged in. And we'll do a quick test again. So we'll just start off with this nut as a spacer. We might need to make this a larger gap. I'm going to have to run this, I would say, for a couple hours just to see what kind of heat we're building up in these diodes. I think the safe operating range is up to 165 degrees Celsius. All right, so we got that snugged up. So we'll get that installed and secured with a lock nut. Though maybe not that one. All right, so we're all connected. We have a spacer. So let's get this installed, starting with the positive brush, which is the one here in the front. And we want to face it that way. So we'll get that secured like that. Then the negative brush. So we'll face that out. And the AC input. So these, again, can go either way. But it is going to be a little bit of a tight fit. Might have to bend that out just a little bit. Like that. Okay. We'll slide that in. And theoretically, that's it. So let's give it a try. All right, let's try this again. I've got you situated here on the business end in case we see any fireworks, but I don't think we will. So ignition's on, choke's on, contact. I think we're looking pretty good. And I guess the big question is, how is this going to hold up under an extended use? How hot is the bridge rectifier going to get? Is it going to cause a failure? And is it going to melt this plastic blank that holds everything into place? So the only way to know that for sure is to put some hours on the machine and monitor it with a thermal camera. So that is something we are going to do. But before we do that, I do want to get the metal oxide varistor ordered up. We'll get it installed, and then we'll bring it outside. We'll do the burn-in test and see how this configuration does. So it's been a few days, and the parts I ordered from Mauser have arrived. We have the metal oxide varistors as well as some diodes. These parts, they're not that expensive. Actually, these varistors were about 15 cents a piece, and the diodes, I think, just under 40 cents a piece. So for less than $3, you could build an entire bridge rectifier identical to the OEM part. And you could actually use these parts to repair the OEM, if the board is repairable. And in most cases, it is. In this case, we're assuming worst case scenario. Either the brushes are destroyed, the board is fried, so you need to come up with an alternative. And this, I think, is going to work out. All we need to do is add the metal oxide varistor into the DC circuit. And ideally, I would connect it down here, by the bridge rectifier. My concern, though, is that this is a tight space when I get it reinstalled and add the extra wires. And there's also a lot of areas that this could potentially short out on. So the safer bet might be to add it onto the brush side. We could solder it directly on the terminals. The only thing you have to watch out for is the heat, that you don't melt the brush holder. But the safer way might be to crimp this right into the terminals with the wire. And that way you don't risk any damage. So let's do that and get this reinstalled. All right, we'll set that aside for now. And the brushes, actually the connections to the brushes, I'm going to rotate them 180 degrees because the bridge rectifier, it's going to be above, not below. But for now, we'll just get the wires off and shorten them to the final length. All right, as far as the varistor goes, I'm going to shorten these leads a little bit less than half of what they are right now, or maybe a little bit more than half. All right, that one's good. All right, so let's test this real quick from the brush to the lead here on the metal oxide varistor on the same side. And we get a nice connection. There should be nothing on the other side because the varistor does not conduct until the voltage, in this case, goes above 750. We have a good connection on the other end. Let's try the other brush. Same thing here. Have a good connection, and we'll check it here on this terminal. And that is also good. So let's get this reinstalled. And I'm going to bend this away from the body a little bit of the stator. Like that. All right, I think we're ready to give this thing a go. I did swap out that plastic piece. The one we installed was made out of PLA, and this starts to soften up at about 120 to 140 degrees Fahrenheit, which is a pretty low temperature. So the one that's in there now is made out of ABS and should be able to withstand about twice the heat before things start to soften up. So we've got the thermal camera here recording, and I'll put that picture on the screen right now. It's a little hard to make out what's what because everything is kind of the same temperature in the generator. But if I point to the bridge rectifier, you'll see the temperature from my hand pretty clearly, and the rectifier is right there. So, when we get the engine started, we'll just keep an eye on things and check in once in a while to see where the temperature is at. So I'm going to get the engine started, and I'm going to put a 1500 watt load on. We'll let things run for a while until the temperature stabilizes. And if everything looks good, we'll double the load to 3000 watts. And I don't think actually the temperature of the rectifier is going to change based on load, because the rectifier, it's providing a fixed amount of power to that rotor. Really the only thing that'll change temperature-wise is the engine temperature and the stator temperature. And some of that could bleed into that bridge rectifier. So let's get the engine started and see what we get. All right, so we've been up and running for about 2 minutes with a 1500 watt load on, and things are starting to heat up. It's a little bit hard to tell looking at the screen out here just because of the glare, but I do see a big red spot where the bridge rectifier is. So, it is expected to get hot, as long as it doesn't get too hot. So I'm gonna let this run for about half an hour, then we'll check back. Alright, we're at the half-hour mark and everything continues to run just fine. Space heater is still spinning. And according to the thermal camera, the bridge rectifier isn't that hot. You know, from what I can tell, it's a lot cooler than pretty much everything else. And if I move the camera and point it right at the bridge rectifier, you know, we'll get a read on the temperature of the bridge rectifier, which is kind of hard to read out here in the sun, but that looks like upper 70s, which is pretty good. That's 79 degrees, I think, Fahrenheit. So if that keeps up, then I think we'll be looking pretty good. So let's double the load to 3,000 watts, and we'll give it another 30 minutes. Well, it's been another half hour and no issues at all. We're still pulling a 3,000 watt load, and according to the thermal camera, the temperature has remained pretty stable. You know, today it's a fairly cool day, about 58 degrees, and the bridge rectifier, it's running at about 77 degrees. So there is a 20-degree temperature rise, which really isn't that bad. That's probably best case scenario. So, you know, I think I've seen enough. So I'm going to take the load off. We'll let things cool down a bit. And then we'll shut the engine down. All right, guys, and that is pretty much it. So the good news is the alternative that we built for the discontinued part seems to work pretty well. So likely this will save thousands of machines, if not tens of thousands. And if you're in the same situation and need to build what we just built here, you know, I will leave links to all the parts used down in the description so you can build your own. You know, of course, if you want to do the easy thing, then that is an option as well. I'm going to be building this as a kit, listing it on eBay with the OEM part, and you can find it there. So, I hope this video helps someone. Thanks for watching.